In the zero visibility environment of dense instrument meteorological conditions, an aviator's survival depends on their navigation hardware. Distance measuring equipment serves as this essential lifeline. This digital aviation panel interface continually outputs three exact metrics: distance, ground speed, and time to station. A novice observing these readouts might assume they function like a modern GPS receiver, plotting a pure two-dimensional horizontal track over the ground. The actual physical mechanism behind the system dictates otherwise. DME relies on active secondary radar to calculate slant distance, the direct line-of-sight measurement from the aircraft down to the ground station. To safely extract data from this panel at high altitude, an aviator must deconstruct the underlying radar physics and manually account for the resulting geometric slant errors. Treating a DME unit like a passive ground track receiver obscures the underlying geometry, resulting in specific, predictable discrepancies between the cockpit display and the aircraft's true position over the ground. The hardware operates exclusively in the ultra-high frequency band, transmitting across specific channels ranging strictly from 962 to 1023 MHz. Unlike primary radar, which passively waits for echoes to bounce off an object, DME is active. The aircraft is equipped with an interrogator unit that forces a direct dialogue with a ground-based transponder by emitting a downward stream of radio pulses. When the ground station receives this specific sequence, it triggers a rigid mechanical timing circuit. The transponder holds the signal in place, imposing a hard-coded delay of exactly 50 microseconds before firing a reply pulse back into the sky. The airborne unit intercepts this reply, measures the total round-trip transit time, and subtracts the 50 microsecond delay. The remaining time reveals the absolute physical distance between the antennas. A severe systemic challenge emerges in crowded terminal airspace. A single ground station can handle interrogations from up to 100 different aircraft simultaneously. The aircraft must isolate its own signal from the overlapping radio noise. The engineering solution is an electronic time gate. The aircraft's interrogator deliberately randomizes the timing intervals between its initial outgoing pulses. This visual timeline illustrates the result. When a storm of replies comes back from the ground station, the aircraft's circuitry acts as a highly restrictive gate, opening exclusively for reply pulses that perfectly match its own randomized transmission rhythm. This randomized gating blocks the replies intended for every other aircraft on the frequency, preventing total data corruption right up until the ground station reaches its absolute 100 aircraft saturation limit. Because those radio pulses travel strict line of sight, they form a right triangle's hypotenuse between the aircraft and the ground station. This hypotenuse is the slant distance. Due to altitude, it's longer than the true horizontal range. The discrepancy peaks directly overhead at 9,000 feet. The true horizontal distance to the station is absolute zero. The cockpit display will indicate 1.5 nautical miles. The radar correctly measures the 9,000 vertical feet of air separating the antennas and converts it into miles, equating roughly 6,000 feet per mile. Aviators rely on a standard operational rule to identify when this slant error becomes mathematically negligible. This graph plots altitude against distance to demonstrate the 1 to 1,000 rule. The slant distance roughly matches horizontal distance only if the aircraft is at least 1 nautical mile away from the station for every 1,000 feet of altitude. Inside this high-altitude cone of confusion, the pilot must mentally discard the DME readout as a horizontal metric, recognizing it strictly as an altitude proxy. The avionics apply this same distance geometry to calculate the secondary display outputs, ground speed, and time to station. The computer derives these figures strictly by measuring the rate of change in the slant distance over time, a mathematical ratio known as the rate of closure. This calculation carries a critical geometric flaw. It assumes the velocity vector points perfectly toward or away from the station. Flying a DME arc breaks this assumption. In a circular orbit, the velocity vector shifts 90 degrees perpendicular to the transponder. Because the distance to the station is no longer actively decreasing, the calculated rate of closure is absolute zero. While maneuvering on an arc, the panel will falsely display a ground speed of 0 knots, completely ignoring the true airspeed. Vector orientation strictly dictates the data validity. Manually managing discrete 3-digit UHF frequencies during a high workload instrument approach is operationally prohibitive. To ease cockpit workload, an automated Vortex system is used. Tuning a standard VHF frequency for a VOR automatically channels the mathematically paired UHF frequency for the co-located DME in the background. Despite this automation, regulatory procedures mandate positive acoustic identification of the active signal to verify data integrity before trusting the instruments. This audio waveform visualization isolates how the paired signals broadcast their Morse code identifiers. The top half shows the VOR broadcasting at 1020 Hz every 10 seconds. The bottom half shows the paired DME broadcasting at a higher 1350 Hz pitch just once every 30 seconds. Isolating this specific high-pitched 30-second audio pulse guarantees that the pilot's spatial geometry is locked on to the correct ground target. By combining the physics of radio waves with geometric vector limits, an aviator constructs a definitive three-dimensional navigational picture. This top-down approach chart shows the VOR component's spatial function, providing a precise lineal radial projecting straight outward from the ground station. The complementary DME component converts the UHF pulses into a rigid circular position line. The exact mathematical intersection of this lineal radial and circular arc generates an immediate absolute spatial fix for the aircraft. Unlike GPS, which relies on processing passive signals from a satellite constellation, DME requires this active two-way exchange with a single terrestrial station. Visualizing these invisible three-dimensional slant vectors allows a pilot to understand exactly where the aircraft is anchored to the Earth, regardless of outside conditions.